Hey guys, welcome back to another A-Level Maths Made Easy video. Just before we get started, most people that watch these videos are not subscribed, so if you ever found anything I've taught or done useful, then I'd really appreciate it if you could just hit the subscribe button, because it really does help me out. I also have space in my A-Level Maths and Physics classes, and if you are interested in that, my email's in the description, but also my website in case you want to see about fees and things like that. And lastly, my email address, as I said, is in the description, so you can use that to ask any questions that might be relevant. Whenever you want, I'm always here to help. So today we're looking at parametric equations, and the first thing I wanted to do is go through why on earth we even use parametric equations. Well, the first reason is probably the most obvious one, which is you can generate graphs of functions that you can't normally generate with using Cartesian equations. So as you can imagine, we can't have graphs going back on themselves with Cartesian coordinates, but parametric we can absolutely do some funky stuff with graphs, which is useful in various applications, but especially with computer science. The other reason is a bit more nuanced, and you probably won't really experience it that much unless you're going to do a maths or a physics-based degree. But essentially, sometimes equations are really complicated to solve or to integrate and differentiate, which is the main thing. So for example, you might have a really long Cartesian equation that's very tricky to differentiate, even using a computer. So if we transfer it into a parametric equation, it can usually be a lot easier and less computationally heavy without losing any relevant information. So let's have a look at what on earth a parametric equation is. This is a parametric equation. Technically, it's plural, but if you notice, the x and y coordinate are not related to each other in the same way. So normally in a Cartesian equation, you have y as a function of x, right? So y is a function of x. Instead, in this equation, in this set of equations, x and y are based on another parameter, another variable called t. So when I sub in a value for t, so for part A it says write down the coordinates of the point on the curve where t equals 2, we sub them, the value of t equals 2, into both equations. So the x coordinate would be 2 squared plus 1, which is 5, and the y coordinate would be 4 over 2, which is 2. Now, this is a set of coordinates in the same way as it is in a normal Cartesian equation. So in that sense, it's completely the same. So for a certain value, so for a certain coordinate, there is one value of t. There can be multiple, but there's one value of t that provides it. You won't get a different value of t for x and for y if it's one coordinate. So that's kind of a key thing there. Again, if you're square rooting, then you can have multiple values, but the idea is whatever you sub in for t into x is what you sub in for t into y as well. And in fact, that's exactly what we're going to use for part B. So for part B, it says find the value of t at the point on the curve with coordinates 5 over 4 and -8. So it makes sense to now set up two equations, right? Sub it in for x. So I've just made x equal to 5 over 4. And we're going to sub it in for y. And you're going to see why we need two equations. So first of all, if I solve this, I'm going to minus 1 from both sides. 5 over 4 minus 1 is a quarter, equals t squared. And then when we square root, we're going to get plus or minus a half. So I don't know if it's positive a half or negative a half yet, which is why they've given me the other equation. Because now, so again, in this case, t is plus or minus a half will give me an x coordinate of 5 over 4. So that 5 over 4, if you notice here, is now going to be mapped to two different values, because there'll be two different y coordinates for the same x coordinate. This is something that we can't normally have in normal functions. So if you look over here, the x coordinate is -5, and we have a y coordinate of, let's say that's 6, and a y coordinate of, let's say, -6. So there's two different y coordinates for the same x coordinate, which we don't normally have. Anyways, we need to find out which one actually, creates this particular coordinate here. So if I solve this, we have -8t equals 4. So t is equal to -1/2. So in this case, t is equal to -1/2, not +1/2. Now, could you have just subbed in the y coordinate and gotten there straight away? Absolutely. And in my opinion, it's better to do that if you have a squared term, or a power of 4, power of 6, etc., any even-powered term, because that way you can avoid getting multiple values. Of course, we can do it with trig functions as well, right? There's no harm in that. Write down the coordinates of the point on the curve where t equals pi over 2. So once again, we're going to do x equals 1 plus sine pi over 2. You can put this in your calculator, or if you remember that sine pi over 2 is 90, that's sine 90, which is 1, so 1 plus 1 is equal to 2. And do the same thing for y, we have 2 cos t, pi over 2. And if you remember, cos 90 is equal to 0, so that would just be 0. So the coordinates are 2, 0. And again, we have to do the same thing. Find the value of t at the point on the curve with coordinates 3 over 2 and negative root 3. Then this is going to get a little bit spicier. We're going to use some of the stuff we learned in our trig lesson in order to work this out. Because, and some of you may have already spotted it, let's say I do the 1 plus sine t is equal to 3 over 2 first, right? So that's the x coordinate equals 3 over 2, so we've done that. That means sine t is equal to half, which means t is equal to something. Now, we could do, so first things first, I need to change my calculator over to radians, shift menu, angle unit, and radians. If we do inverse sine of a half, some of you, the more eagle-eyed among you, have noticed that there's actually more than one value. In fact, there's an infinite number of values. So I need to actually work out a few values and see which one is the actual same as when it's cos. So, yeah, I mean, let's just work out the other values, right? So with sine, if you draw the graph, again, I do want to do another video on actually using the graph instead of using the cast diagram. I think the cast diagram is an absolute waste of time. And all it is a simplification of the graphs anyway. It's just worse. We've got our first value here, which is pi over 6. This value here is, of course, pi over 2. The other value is there. Now, the interesting thing about the sine and cosine graphs is that they're symmetrical. So going from 0 up to a half is a distance of pi over 6, which means going from a half down to 0 is also a distance of pi over 6. So in other words, that value here is pi over 2 minus pi over 6. Can I do that in my head? Probably, but let's not be arrogant. Let's just quickly use a calculator. So pi over 2, subtract answer, gives me pi over 3. And of course we can work out other values as well. We can keep going and find lots of other values. Hang on a minute, that's not pi over 2, that's pi, because that is 180 degrees, not 90 degrees. So pi minus pi over 6 gives me 5 pi over 6. I knew that seemed wrong. I need to practice my radians, apparently. And we can do the same thing with cosine. So we have 2 cos t equals minus root 3. So it means cos t is equal to minus root 3 over 2. So t equals, by the way, this is where the cast diagram really starts to fall over, because finding negative values and negative angles and doing all this fun stuff is a pain in the butt. It really is. It's a pain in the backside. So I would recommend using the graphs. If you guys want a video of me using the graphs to show you how easy and awesome it is, I really don't mind doing that either. And if you notice, we have a value that matches. So that must be our answer. It must be t equals 5 pi over 6. If we found the other values for this, by the way, we'd see that they don't match with the t values from here. So that's just a quick check. So, I mentioned before that parametric equations aren't always used in order to get equations that we've never seen before. That's not what we always use them for. Instead, we actually use them for other reasons as well. Namely to simplify equations, if you remember what I said at the beginning. This means that we can sometimes, I'm going to say usually, at least for the purposes of A-level maths, we can convert parametric equations into our Cartesian equation. Remember, the definition of a Cartesian equation is that y is equal to a function of x. So all we want to do is eliminate t from the y expression, or the y function. So if I rearrange this, I get x over 3 equals t. I can sub it into here and get y is equal to x over 3 squared, which funny enough would actually just be the answer, but I like to simplify my expressions. that is a Cartesian equation that will look exactly the same as this set of parametric equations. How nice is that? Again, in this case, do I think it's simplified? Not really, to be honest, but that is what they use for. And again, we could do the same thing here. We could rearrange t for an expression with x in it, and then sub it into y. So here we would have t equals x plus 1 over 2. So that means y is equal to 2 over x plus 1 over 2 squared. So I'm going to expand that. We get 2 over... I might leave this as x plus 1 squared, just because it's not going to look any nicer if I expand the quadratic. And then when you're doing this, in case you're a bit unsure, the way you would do that is you would separate it into this. X plus 1 squared over 4, keep flip change, 1 squared, so you get 8 over x plus 1 squared. And I don't think expanding the brackets would be important in this case, because I don't think it would actually provide any kind of use, I suppose. And lastly, again, something a bit harder, rearrange it for an expression where you have t equals something, basically. So we would have here, if I swap those around, you'd get this. Now the question is, do I want to combine these two things? Do I want to combine them? If I look ahead a little bit, it would be beneficial not to, because the 1 will combine with the 2 anyway. So let's sub that in. We get 1 over 2 minus 1 over x. Don't forget that's a minus 1 now, because that minus goes around the entire of t. So that becomes y equals 1 over 1 minus 1 over x. We should definitely combine this. Could we leave it like that? Maybe. The question didn't say to simplify, so technically I'm in my rights to not do it. But let's just be good mathematicians and assume that in an exam, maybe the question would say that. I could, that's equal to 1 over 1 minus 1 over x. So times top and bottom by x. And you get x minus 1 over x. Keep flip change again. We would get 1 times x over x minus 1. So you just get x over x minus 1. If you just look at this, by the way, this is just taking the reciprocal anyway. So either way you did it, you would get that kind of function, which is a lot nicer than this disgusting looking thing here. Now, of course, this is A-level maths. You're probably aware by now that it's never that simple, ever. So, we can also change trigonometric functions into Cartesian equations. And how do we do that? Well, this is a really good question. If you look at this, I'm going to show you some of the most common ways to do it. I wouldn't really expect anyone to be able to look at this and go, oh, you do this. I wouldn't expect anyone to do that. I'm not an unreasonable person. But, again, so I'm going to go through the most common examples using, cosine and sine and cosine of double the angle, and then something a bit crazy on the end. This one, the only identity that relates cosine and sine is this one. And that's exactly what we're doing. So that is y squared plus x squared equals 1. You get some brownie points if you recognise what that is. That is the equation of a circle. Which, by the way, is how you get the cast diagram. So if you notice with the cast diagram, in your textbook, in the year 12 textbook, there's a big circle. They use this identity in order to produce the cast diagram. Anyways, so how do we do it with the cos 2 theta? Well, just so you know, for your exam, you do not get the double angle formulas, but you do get the addition ones. So I personally don't memorize the double angle formulas. I just memorize the addition ones because that makes more sense to me. So if I write this out, we get x equals sine theta, and we get y equals, that would be cos theta plus theta. And if you remember the the addition formula, it's cos A cos B minus sine A sine B. So in other words, if they're both the same, it'd be cos theta minus sine theta. So that would be cos squared theta minus sine squared theta. Now we don't have cos theta, we have cos 2 theta. So instead, I'm going to rewrite this eliminating cos squared. Because I have sine, it's x, so that's x squared. but I don't have cos theta. It's not just half y, which I have seen people put before. So instead, I'm going to change cos squared theta into sine squared theta by using the identity that sine squared theta plus cos squared theta equals to 1. Rearrange for cos squared, we get cos squared theta equals 1 minus sine squared theta. Sub that in, we get 1 minus sine squared theta minus sine squared theta. So that is y equals 1 minus 2 sine squared theta. And remember, we know that x is equal to sine theta, so we get y equals 1 minus 2x squared. That's a fun one, isn't it? But hopefully that makes a bit of sense. The type of thing you're going to be expected to be able to do. Anyways, then to the last one. How do you do something like this? Well, remember, in the first case, we used sine squared plus cos squared because we had cos and sine. We had cos theta, we had sine theta, so we could use sine squared theta plus cos squared theta. In the second question, we did not have cos theta. We had cos 2 theta. And so we couldn't use sine squared plus cos squared as 1 because they had different angles. So I used the double angle formula, well, the addition formula really, to just get it in terms of sine. In this question, this looks scary, but if you notice, we do have cos theta and sine, oh, that's bad by me, and sine theta. That is meant to be a theta, I promise. I didn't notice that before. So what if I just rearranged for sine theta and cos theta and used the same equation? So again, here's the logic. Whenever you're combining sine and cos, if they have the same angle, cos theta and sine theta, always use sine squared plus cos squared as 1. If one of them has the double angle in there, expand it using the double angle formula and try and get just sine theta or just cos theta or just both of them. In this question, because we have cos theta and sine theta, we can just rearrange. That's the easiest way to do it. So here we would have x minus 3 over 2 equals cos theta. So minus 3 from both sides divided by 2. And here we'd have y minus 1 over 2 is sine theta. Because I'm minus 1 from both sides divided by 2. So now again we use sine squared theta plus cos squared theta equals 1. This is the formula we always want to use, or the identity we always want to use, if we can. So, now here's the big question, right? Do I want to simplify this? Honestly, no. Bearing in mind that this is indeed it's just a classic equation of a circle. If I want to make it look like an equation of a circle, something that I could do is I could times everything by 4. Now, why am I timesing by 4? Inside these brackets is an over 2. So if I expand that, we'd go over 4. Over 4 equals 1. Normally, we don't see fractions inside the brackets with an equation of a circle. It's not necessarily wrong, but this looks much more like an equation for a circle than the other thing, because now the radius is just 2 instead of 1. Nice and easy. But yeah, hopefully that doesn't scare you too much. Trig is ugly. People don't like trig, but it can be quite elegant once you get a bit more used to it. Okay, I know what you're thinking. Come on, Mitchell. Come on, man. That's the easy stuff. Give me the hard stuff. Okay. Well, I would like you to pause the video and have a go at these two if you think you can, if you think you're man enough. But if not, I'm going to go through them nice and quickly. So this, again, ideally we want to use sine squared plus cos squared as 1, but we only have sine. This is the double angle formula again. It's sine 2 theta. So again, remember, I don't like memorizing any formulas. So that would be, it would literally just be sine theta cos theta plus sine theta cos theta. So in other words, equals 2 sine theta cos theta. Again, I don't bother memorizing them. I don't think you should either. But we are going to expand in terms of that, because don't forget y, when we have sine squared, it means this. We're literally squaring sine 2 theta. So if I do that now, we get 2 sine theta cos theta squared. So if I quickly expand that, now I just want to make sure oh God, I think I just had a stroke. To keep you rest assured that this is all one step. Again, my instinct, the second I see a double angle, is to expand the double angle into its components, because now we just have sine theta and cos theta. The only other information we have is x equals sine theta. So we can't apply it to a double angle. We have to get rid of it. So now we're closer, because now we have sine theta, which we could sub in x for. So this is just 4x squared. Cool. But we don't have cos squared theta. Think for a second. What did I do when I had a cos squared theta and I had sine theta and I wanted to get rid of cos squared? I used sine squared theta plus cos squared theta equals 1. So again, all of maths, all of this proof stuff, all of this show that, all of these trig identities, it's all about what do you have, where do you want to get to, what can you use to get there. If you keep looking at what you need to get, or keep thinking about what you need to get, it becomes 10 times easier. I have cos squared, there's nothing I can do with cos squared. I have sine theta, I need sine theta. Well, cos squared can become sine squared. So that's the thought process going through my brain, always. And then I'm subbing that into here. So we have y equals 4 sine squared theta. I'm going to use brackets because I'm not a degenerate. And again, x is just equal to sine theta. So this is the same as saying 4x squared, 1 minus x squared. That's a quartic equation right there. How juicy. Now, this is what's going to separate the men from the boys, so to speak. How about that one? Well, this one's a bit trickier. As I've said before, ideally we want to use sine squared plus cos squared equals 1. Now, we have tan squared. I'm hoping that's triggered some alarm bells in some of your heads, because there is a version of sine squared plus cos squared that uses tan squared. Now, the tan squared and the cot squared formulas, or identities, you do not get given those in the exam. So instead, I use this and I show you how I derive them. Sine squared plus cos squared is 1. We want tan squared. I'm going to divide the equation by either cos squared or sine squared. I have to make that decision, but I'm dividing it by one of them. Which one will give me tan squared? Well, if I divide by sine squared, I'll get 1 plus cot squared equals sec squared. Cosec squared. However, if I divide by cos squared, I get sine over cos, so that's tan squared, plus 1 equals 1 over cos squared, which is sec squared theta. Okay? That's it. Do not memorize. Memory is pointless. It will betray you. It's awful. Instead, think about how you can get to the answer. Start with sine squared plus cos squared is 1. Divide by cos if you want tan. Divide by sine if you want cot. That's it. And by the way, like, something that I did in my exam is literally as soon as they said go, I wrote sine squared plus cos squared is 1, and I derived the other two. So I divided by cos squared divided by sine squared, so I could check for the sec and the cosec as well. Why not, right? So, using that, we know that y is equal to tan squared, but we have sec squared here, but we have x here. Well, what if I just took the reciprocal? That means 1 over x equals 1 over cos theta. Right? I could divide both sides by x, divide both sides by cos. Right? Which means 1 over x is equal to sec theta. So here we have y squared plus 1 equals 1 over x squared. Then all we're doing is we're moving it to one side. Oh, sorry. Whoa. Y is tan squared, so it's y plus 1. So y equals 1 over x squared minus 1. That's it. Not too bad, right? Hopefully, maybe, possibly. So, to finish off, this is an actual exam question. Look at that little goldfish alpha looking thing. Actually, it's more like an alpha, I suppose. And these are the Cartesian coordinates. So, the parametric equations that represent this equation, this parametric graph here. And it says the curve C cuts the x-axis at points A and points B. Find the x-coordinate at point A and the x-coordinate at point B. And here's where students start complaining. this is not too bad. In fact, you solve it in the same way that you solve the same question on our Cartesian graph. So it says that it cuts the x-axis at A and B. So what is the y-coordinate? Y equals 0 for both of these. Because some people, and this baffles me, they start trying to solve this. What? What are you doing? What are you doing, you silly goose? No. Instead, you want to use the information they've given you in the same way that you do with Cartesian. Y equals 0. So I'm going to sub in y equals 0 here. Okay. So we have 0 equals t 9 minus t squared. So to solve this, I'm going to factorize that using the difference of two squares. So it's 3 minus t and 3 plus t. So my solutions there are t equals 0, t equals 3, and t equals minus 3. Now looking at the graph, which one does it seem to be? Well, that's a pretty good question, to be honest. I don't know. The common mistake I see is that people say, t is minus 3 here, plus 3 here, and 0 somewhere else. Well, that doesn't really work, because t is not represented on a graph. It's not, which is the weird thing, right? Because normally x and y are represented. I mean, x and y are still represented, but t is not. So instead, what we have to do is sub in these three values of t into x and decide by looking at them which one it seems to be. So, hopefully that makes sense. Let's start. So when t equals 0, we have x equals 5, 0 squared minus 4, so that's minus 4. Cool? When t equals, let's say, minus 3, we have x equals 5 minus 3 minus 4. So minus 3 squared is 9. 9 times 5 is 45. 45 minus 4 is 41. And when t equals plus 3, x equals, it's going to equal the same thing, isn't it? But, you know, in for a penny, in for a pound, we get 41. Now, to think of why this happens, keep in mind that we actually cross the x-axis twice at the same place. That's why there's three solutions here. One of them is at A, but then if you notice, this part of the curve goes through B and this part goes through B. So we get two solutions at B with the same x-coordinate. So in other words, the negative x-coordinate is of course A, but also the repeated x-coordinate must be at B, because that's where it happens. So in other words, we have our coordinates for A are minus 4, 0, and for B, we have 41, 0. And that's it. So again, using the graph, using the exact same tricks, we can work out what the hell we need to do. And yeah, like, don't panic, man, it's all good. It's all good. Yeah, if you guys found that useful, and if you want me to do, so keep in mind, something that I did see on a couple of the comments is, I don't go super hard in these videos. The point for these videos is to introduce the topic to you, because I think that A-level teaching can be kind of crap sometimes. So this is just to teach the topic. I will have an aiming for A star. If you look back, I've already made some of the A star videos where we go through the hardest questions from all the topics. These are old spec questions, new spec questions, university questions. They are the hardest of the hard. The hardest thing you'll ever see. In fact, the thing in the exam will be easier. I do have some of those videos already, like aiming for A star videos. If you look back on the channel, I do have them. But I will be making those for all the topics shortly. This is just to introduce the topic to you, to teach it to you. The aiming for A star stuff will come later. But if you found any of this useful, please consider subscribing, sharing, liking, all that fun stuff, because it really does help me out. But I will see you in the next one. Have a great day.